Okay, so can everyone hear me? All right, great. So an interesting phenomena is happening, which is that the number of participants currently logged in is 14, but the number of registrants in the course has gone up to 45. So I'm not sure if that means that a lot of people have decided to participate asynchronously, or whether people are just a little bit behind, or we'll see. Anyways.
Super anecdotally, I know one friend who has a conflict with like the first half hour, and so he's going to be watching the recording later.
Okay, fair enough. Was anyone able to access the recording of the first lecture? Did anyone check that? I posted it on Zoom. Okay, great, thanks. I posted it on the Canvas along with the whiteboards, which was a bit of trouble. The whiteboards, they came out in some random order, and they were little tiny thumbnails, so I had to figure out what the correct order was. But anyhow, it's ordered correctly now. Okay, so let's see. I put up the 0th and first assignment. So the 0th assignment, which is due Monday, is if you're planning to come back to send me a short note saying who you are and what kind of program you're enrolled in, and if you have an advisor, who your advisor is and what institution and so on, and also what sort of math you're interested in, why you're interested in the course, and what kind of mathematics background you have for the course, and some interesting fact about and memorable fact about yourself. So if the course was smaller, then we might do it in a round, but when the registration went up to 45, I decided it was better to have people submit this on Monday, and then the actual assignment is due the following Monday at midnight, and it's basically a little bit of background stuff, a little flavor of Riemannian geometry, a little flavor of linear optimization, a little flavor of functional analysis, just to sort of see where everyone stands, because I think it's a very mixed audience, likely. Are there any questions? Okay, so let me see. I guess on Tuesday, I talked about Monge's problem. And so I want to take some steps towards explaining how to solve it today. So Monge's problem was we're given two probability measures on spaces m plus and m minus. On Polish spaces m plus and m minus. And we're given, say, a continuous cost function. And we want to look at maps G that push forward mu plus to mu minus, and the cost associated to such a map is the total or the expected value of C of x, G of x, integrated with respect to the mass being produced at x. And then Monge's problem was to minimize this among all maps that push forward mu to mu minus, if any such maps exist. And so let's see, are you still seeing me? Am I still the speaker? Yeah, okay, good. As I mentioned on Tuesday, oh yes, by the way, so somebody on Tuesday, Trong, I think it was, mentioned that Luigi Ambrosio and two of his former graduate students have a new book out, which in 2021 called Lectures in Optimal Transport. So I had a look at it between Tuesday and now. It's very nice. It's available as an electronic resource from the University of Toronto Library and perhaps other libraries. And yeah, I think it's a good source for, especially I'm gonna try to simplify my life by assuming mu plus and minus are compactly supported, and C is continuous. And if you want to see how things are done when mu plus and minus are not compactly supported and C is maybe only lower semi-continuous or something, then Ambrosio's lecture notes are a perfect place to see that, as is probably Sant'Ambrogio. But Ambrosio's lecture notes are also nice for explaining why we want M plus and minus to be a Polish space and so on, and showing basic facts like if you have an open subset of a Polish space, Polish space is supposed to be complete. If you take an open subset of Rn, it's not complete anymore in the usual Euclidean metric, because you need to add its boundary to make it complete. But Ambrosio shows that if Rn is a Polish space, which it is, then you can define a new metric on any open subset, which makes the open subset complete. I think there's a sign error in his metric, but anyways. So this was Monge's formulation from 1781. And it was actually kind of a well-known problem. It was proposed for a prize in the 1800s, which was claimed by Paul Appel. But the next big bit of progress that everybody remembers came in the middle of the first half of the 20th century, when Kantorovich figured out how to reformulate this thing as a linear program. But maybe before I do that, let me sketch the discrete analog. So what would the discrete analog be? Anyone want to take a guess? Use Dirac measure. Yeah, that's a good idea. So are you from Austin, Texas? Is that what I remember?
Yeah, I'm from UT Austin.
Oh, great. And are you working with someone there?
I was working with Francesco Maggi.
Okay. So yeah, so the natural discrete analog is, you think about the case where maybe both mu plus and minus are given as sums. Let's see. So let me introduce a bit more notation. If n is a positive integer or a natural number, I'm going to let brackets n be the set of integers from 1 up to n. And so mu plus could be a sum of, say, n plus discrete masses. Located at points xi in m plus. And then to make it a probability measure, I'd better divide by m plus. And similarly, mu minus could be a sum of discrete masses. And potentially, you could have, you might insist the numbers, you might insist n plus equals n minus or not. But actually, the case n plus equals n minus is kind of nice, because then instead of a mapping G, you would seek a permutation. Permutation sigma on n letters, minimizing, so let me call that sigma n, the sum of, well, let's Cij be xi plus xj minus, and then we'd be trying to minimize C of I sigma j, sigma I rather, I counting from 1 to n. So that would be one reformulation. And this is still not so nice, because you still have to look at n factorial permutations. So a simpler thing from a computational point of view, you can replace the sigma, the permutation sigma, by a rectangular matrix, or a square in this case, but rectangular in general, whose column sums and row sums are given by these coefficients here. What shall we call it? I guess I can call it Sij. I guess that I didn't need to make these. I chose to make the weights all equal. I could have put if I took this out, I could also put mi plus and minus, where the sum over the mi plus equals 1 and the sum of the mi minus equals 1. So I could have put other weights that add up to 1, as long as the mi plus and minus are non-negative. And so you would replace this sigma by a matrix whose column sums and row sums add up to these weights. I think I need to go to a new whiteboard. Anyone want to take a screenshot before I do? I will try to put the whiteboards up after lecture again next class. So, so I want the sum as I counts from 1 up to n plus of Sij to be the mu minus of j, and I want the sum as j counts from 1 up to n minus Sij to be the mu plus of I. And the other thing I want is that the matrix be non-negative. And then, so let me call, I guess, capital, capital S is going to be the set of these non-negative matrices. Should be, you normally write it the other way. And then you can minimize over matrices S in capital S. And the cost would be whatever it was before. And then you'd weight the Cij by the amount of stuff going from the ith column to the jth row. And this would be a sum on I and j. So somehow that's the total cost. And this is a much nicer problem because the set S is a convex subset in our n plus cross n minus. And it's also bounded because the numbers are all non-negative here and they add up to 1. If you add up all the entries in the matrix, they add up to 1. And it's closed. And that's great. So we're now minimizing over a compact convex set. And we're trying to minimize an expression that depends on a linear way in S. And so this is a so-called linear program, i.e. And there are lots of good algorithms and techniques for solving linear programs. Linear minimization on a convex set. In this case, compact as well. And it's even, it's even given by finitely many constraints. So it's not, it's even a compact convex polytope. And so now you're in better shape because and oh yeah, by the way, how do you how do I know? So of course we'd like the minimum, we'd like S to be non-empty, but how do I know it's non-empty? Shoot, I'm screwing up my view here. There we go, that's better again. So why should this set be non-empty?
Well, the conditions are equivalent to multiplying by a vector of 1s, I think, and then it has to be equal to a certain vector. Is that correct?
Yes. Mm-hmm. So Right, when you can, so the conditions on the, I've boxed myself into a corner with my notation here, but right, so one way to say the conditions is that if you multiply S by a vector of ones on the right, you get the vector whose elements are the M pluses, and if you multiply it by a row vector of ones on the left, you get the, I may have the plus and minus backwards, but you get the row vector whose elements are, so I should, this would be a column vector and this would be a row vector. Right? So what about if we think about the case where all the weights are the same, so that I'm asking that, so n plus is equal to n minus is equal to n, and I'm asking that every row sum to 1 over n and every column sum to 1 over n. And all the entries are non-negative. Can you think of a matrix that does that? An n by n matrix that does that?
Identity, and you scale it by 1 over n. Does it do it?
That's right. No, carefully. If you scale the identity by 1 over n, you add up all the rows, there are n 1 over n's in that row, they add up to 1.
Right.
So how do I make the columns in the row all add up to 1 over n? That was very good, though, very close. Yeah, someone says, oh, what do you see? An S by multiplying and renormalizing. Yeah, I'm happy to let the sums of, these are probability measures, so the sum of the MI and the MJ are both 0. And yeah, multiplying. So what's in the numerator there is, exactly. So if you look at, for this case where I want all the columns and rows to sum to 1 over n, then I put 1 over n squared in every position. And since there are n positions, when I add up n 1 over n squareds, they add up to 1 over n. And so more generally, you would do exactly what Joachim said. More generally, you would take Sij to be mi plus times mj minus. The denominator would be 1. And as long as the sum of the mi's pluses is 1 and the sum of the mi minuses is 1, that works. And so then you're in better shape because you know at least you're doing a minimum over a compact of a linear function over a compact non-empty convex set. And so first of all, the minimum is attained because continuous functions on compact sets always attain their minima. And secondly, you can, because it's a polytope, you can even say that, you know, you slide down this linear function to, you'll hit the boundary of the polytope eventually. And you might hit a corner or you might hit a face, but even if you hit a face, the face has corners. So at least one of the minimizers will be a corner, or what's called an extreme point. So the conclusion of this is min is attained at an extreme point. And so if we then wanted to go back and think about, in this case where all the columns and rows sum to 1 over n, we could go back and ask, okay, now we know that a minimizer exists in this more flexible sense where, I didn't say it, but Sij is the fraction of mass at I sent to j. And so we weight that fraction with the cost of shipping from I to j. And then we can go back and ask, is the minimum really attained by a permutation or not? Or do I really need to split, in order to achieve this minimum, do I really need at some i's to split the mass and send a bit of it here and a bit of it there? And so one of the questions on the first homework assignment is to show that in this case where the columns and the rows sum to n, that this polytope actually has n factorial extreme points and they correspond to the permutations. And so you might hope to implement an analogous strategy in the continuous case to solve Monge's problem, which is sort of what Kantorovich did. And life is, I mean, you make a lot of progress by doing that, but life is not quite so simple because it's not quite so easy to characterize the extreme points of this polytope. Nevertheless, I'm going to create a new whiteboard. Nevertheless, what Kantorovich proposed around 1942 was, given these two probability measures and the cost, seek a joint measure. I'm going to call it gamma. So this is now it's going to be a non-negative measure on the product space, m plus cross m minus. And it's going to have the property that if I project all of its mass onto the first coordinate, I'm going to see mu plus. And if I project all of its mass onto the second coordinate, I'm going to see mu minus. So in other words, mu plus of u is going to equal gamma of u cross m minus, and gamma of m plus cross v is going to equal mu minus of v for every u cross v in m cross m minus Borel. So this having prescribed another way to write this. So this is also the set of non-negative measures on the product space, such that if I project onto the first coordinate, I see mu plus, and if I project onto the second coordinate, I see mu minus, where p of x, xy is x, and so this should be capital, I guess. P of y, xy is y. So this is somehow, this gamma is going to be the analog of the matrix Sij, and these conditions are the analogs of the column and row sums being prescribed, and associated to each such gamma is a total cost. The cost of gamma is going to be just the integral over the product space of our cost weighted by gamma, our given cost weighted by gamma. And so Kantorovic's problem was basically minimize this cost over all these joint measures having the prescribed marginals. And so I'm going to call this WC again. And some of the nice features that we saw in the street example persist in this kind of continuing setting. So this cost is, again, depends linearly on gamma. And this function, this set of joint measures with prescribed marginals is convex. In other words, any two gammas which have the correct marginals, their average, again, has the correct marginals. And so I guess we don't know the min is attained yet, so it's an infimum. But the good news is that, so what we would like to do is we'd like to know if we could find a topology which makes this convex set compact. And so there should be few enough open sets for this convex set to be compact, but there should be enough open sets for this functional of gamma to be continuous. And then we would know by whoever's principle it is, Bolzano's principle, the Bolzano-Weierstrass principle, that a continuous function on a compact set attains its minimum, also attains its maximum. So, and this kind of situation comes up over and over again in analysis and partial differential equations, that and calculus of variations is some part of the art is to find a topology. You're trying to minimize some functional. You want to find a topology that's rich enough for the functional to be continuous and sparse enough for the set that you're minimizing on to be compact, and then you know a minimizer exists. Rich enough for cost gamma to be continuous and sparse enough for capital gamma. Sorry, to be compact. And if you can find such topology, then you're in good shape, because at least a minimizing object exists. And then you can start to worry about its structure. Is it really, do I really need to, are there a positive fraction of locations at which I really need to split the mass and send the output from a given mind to factories, or will it be true for almost every initial location that all of its mass gets sent to a single final target? So that's somehow after you take the solution of Kantoorovich's problem and you try to deduce by analyzing it whether or not it also solves Vonnegue's problem. That's the strategy. Other questions? And so in finding such a topology here, we're helped by functional analysis. So functional analysis is very well adapted to linear problems in infinite dimensions. So there's a huge body of theory for linear problems in infinite dimensions, and much less theory, or it's much more of an art these days to deal with nonlinear problems. But for linear problems, things are pretty well worked out. And if we are willing to assume the cost depends continuously on x and y and that the measures are compactly supported, then it's fairly straightforward. It's a little bit more delicate if you want to deal with measures that may extend to infinity. Then you need the cost to maybe not grow too quickly at infinity, or you need additional arguments. But in fact, it's enough that the cost be lower semi-continuous and the right. In fact, I think that as soon as the cost is lower semi-continuous, the infimum is actually attained. But maybe I don't want to bother you with lower semi-continuity at this stage. So so if lower semi-continuity C is enough to ensure inf is attained, but for simplicity, take C to be continuous, and U plus and minus compact. Oh yeah, so I should say, what do I mean by the support of the measure? Support mu minus minus compact, where by support of mu plus, I basically mean the smallest closed set of full mass. So in other words, that's the intersection of all set C such that C is closed, and mu plus of the let's say mu plus of C is equal to 1. So it's clear, you take an intersection of closed sets, you get a closed set again, and you need a little argument to show that this intersection still has mass 1. And then somebody, so yeah, then what is the functional analysis involved? So the functional analysis basically says, then we might as well take M plus and M minus to coincide with these supports. So we can take these to be compact sets as well. And so basically the functional analysis is, goes by 2 steps. So if we look at the continuous function, let's take, so this compactness here implies, without loss of generality, M plus and minus are compact as well. And so if I look at the Banach space of continuous functions on the products, well, okay, let me not even worry about the product. If I look at the Banach space of continuous functions in M, and I put the supremum norm on those continuous functions, that's a Banach space. And it has a dual space. So if you know what the Banach space dual of the continuous functions in the supremum norm is, raise your hand. Or yeah, raise your hand. By the way, has anyone noticed that I see a couple of hands up, but not that many? Has anyone, so the new version of Zoom, I see some people are putting their hands up physically and other people virtually. The new version of Zoom can tell if I can raise my hand physically. Sometimes it pops up virtually. I found that very disconcerting that when it first happened to me. AI in action. Okay, so one of the 3, let's say let me see. How about Thian Dang? Okay, what's the Banach space dual of this guy? Maybe I mispronounced your name. So one of the people with their hands up is someone named Thian Dang. Oh, here it is. The space of Radon measures. Okay, great. It's in the chat. Yeah, so this is basically the Rees-Markov theorem. Says that the Banach space dual consists of the measures on M plus and signed measures on M plus, and the dual norm star, let's say, is what's called the total variation or the total mass norm. So you take the mass of the negative part and the mass of the positive part and you add them up, and that's the total mass. Do you have a question, Thuyan, or you still have your hand up? You just haven't put it down yet. And so that's one important theorem from functional analysis, which maybe some of you have seen the Rees representation theorem. It says in certain contexts when you have a linear functional acting on continuous functions that you can write it as the integral of that continuous function against a measure. That's what this is doing here. And then the other big machine that we need is that in finite dimensions, in the matrix problem we looked at, we know that closed bounded sets are compact. That's the Heine-Borel theorem. And unfortunately, now we've moved to infinite dimensions, spaces of continuous functions, spaces of measures. And it's not true that closed bounded sets are compact anymore. However, there is a central compactness result, which I call the Banach, is usually called the Banach-Ala-Oglu theorem, which says that whenever you have a dual Banach space, what does it say? So if X and its norm are a Banach space, then the unit ball in the dual space, which is usually the dual space is usually denoted X star and norm star or whatever, or norm X star, is weakly compact, or weak star compact actually. And so I have to say, what does this weak star compact mean? And so in particular, it's not generally norm compact. That's the bad news. It's not compact in the norm topology on the dual space. The unit ball, which is a closed bounded set in the norm topology, is not a compact set in the norm topology, but it is compact in some other topology. And so let me just make, no, I guess I don't want to erase for later purposes. Okay, so new whiteboard. I.e., oops, okay, that's fine. I.e., oops. Let's say, so we're now in the dual space. So a sequence or a sequence of elements in the dual space, or a net of elements in the dual space, converges to a limit, weak star, if and only if, for this is now in the dual space, for every X in the original space, the dual is a linear operator, so lambda of X is a number, real or complex. This limit is 0. So it basically, so it doesn't say anything about the norm or the difference between the elements in the sequence and the limit, but it says that after you evaluate on some point, then the limit of the difference in the numbers converges to 0. And so that's the sense in which the unit ball in a dual Banach space is compact. And now if we go back a slide, we realize that tells us that the unit ball in this space of measures is compact. And it's compact with respect to total mass. So in particular, if we look at probability measures, they all have mass 1. So what it means to be so the probability measures all live in the unit ball over here. And so that's good because we were trying to minimize over, if I go back another slide, we were trying to minimize over a set of probability measures, namely this set capital gamma. And so this set capital gamma lives in the unit ball of an appropriate dual space. And so, and more, okay, right. Okay, great. So that's somehow the strategy. And so let me write it down. I want to go forward a couple of slides. So where to? I just want to create a new one, basically. Oh no, here we are. So now gamma mu plus minus is contained in the set of, in fact, non-negative measures on M cross minus, which is contained in the Banach space dual of C. And because, sorry, it's even probability measures. Let me make this probability measures. And so this is in the unit ball. And so then, so now we're, as long as this is weak star closed, then it's weak star compact because a closed subset of a compact subset is compact. And so we claim that actually gamma mu plus minus is weak star closed. And the linear functional cost gamma is weak star continuous. And I have sort of left this for the first assignment, checking that this is weak star closed. In a little bit more generality than this, I think I've also left you to worry about what happens if the mu plus and the mu minus are not compactly supported. And of course, this cost is exactly the action of, so this is exactly like lambda of x, where we identify x with C and lambda with gamma. And so this is exactly continuous because that was the definition of the weak star topology, was that if we had a sequence of measures here, gamma, we'd be evaluating at a point x. And so if gamma n is converging weak star, then these numbers are converging. If gamma n is converging weak star, so weak star convergence of gamma n to gamma infinity tells you these numbers are converging to this limit. And so that's what continuity of the cost is. Okay, questions? Okay, so if you accept, or if you know or accept this kind of functional analysis, then there's this is the topology up here, which allows us to deduce that a minimizer has to exist in the Kantorovich sense. Great. And so now we can start to wonder, what does that minimizer look like? And we'll be very interested in what can be said about the support of the minimizer gamma, which is some subset. It's the smallest subset of the product space that has full mass. Because the support of gamma is, each point xy in the support of gamma is basically telling you that a fraction of the mass near x goes close to y. So it's telling you who's supplying who. And Monge's question, in a sense, is, can I insert into this, so somewhere between m plus and m minus, can I insert, so I know this is contained in m plus and m minus, but is there the graph of some function in here? Or at least contained gamma almost everywhere. So if the measure gamma lives almost surely on the graph of a mapping G, then G was going to solve the Monge problem for us. Does that make sense? If I think back to the one-dimensional problem that we talked about the solution to on Tuesday, so if you solve this Kantorovich problem in one dimension for a cost that was a convex function of x minus y, like the pth power where p is bigger than 1, you would find the optimal measure gamma for Kantorovich's problem. It's a measure on the plane such that if you project onto the horizontal axis, you see mu plus. If you project all its mass onto the vertical axis, you see mu minus. And if you choose it to be optimal, for a strictly convex cost, then then the entire mass of that gamma is going to concentrate on a non-decreasing subset of the plane. And what it means to be non-decreasing is if you take any 2 points in it, the change in y times the change in x is non-negative. And non-decreasing subsets, except at countably many points, where they might be vertical, they lie on graphs. And so as long as your measure mu plus is not charging any individual point on the line, then almost surely you have containment in the graph of a non-decreasing function, and that's the solution to Monge's problem. And so somehow, to get Brenier's theorem, we'd like to show a statement like this in higher dimensions that almost surely support gamma is contained in the graph of the map. Okay. Oh, and I skipped a point. Which, so we talked about, if I go back to my previous slide, we talked about the Kantorovich problem being set on a convex set, which is compact in a suitable sense. But I guess we also want to know that that set's not empty. So what measure would live? So how do I know that this set is not empty?
I think the product measure is inside this set, right?
Exactly. So that's one example of a measure that, because these are probability measures, one example of a measure that satisfies all these conditions here for every Borel thing is e.g. mu plus cross mu minus. The product measure, the thing that is in gamma, where by mu plus cross mu minus, what I mean is the measure that if I evaluate it on some rectangle u cross v, it's just the product of mu plus on u times mu minus on v. So already Kantorovich problem is better than Monge's problem because we know that the things we're minimizing over is not empty, even before all the functional analysis. Okay. Fast forward. So let me see. Right. So let me muddle forward. So maybe I can. So I'm going to foreshadow a little bit. So there's the big theorem of Kantorovich is the so-called duality theorem, and maybe I'll write it down, but then I won't say too much more about it until probably next lecture. So the other thing Kantorovich figured out, and he figured this out first for the case where the cost satisfies the triangle inequality, and he wrote it down, says that WC mu plus mu minus, which we define as a minimum over some things, is also actually equal to a maximum of something else. It's also actually equal to a supremum of integral u d mu plus integral v d mu minus, where u plus v is less than c. U of x plus v of y is less than c of xy for every x and y. And probably I want u to be L1 d mu plus and v to be L1 d mu minus. So actually, he wrote this down, and he sort of said, at least in the 1942 paper that I read, he said, he wrote it down in a slightly different form, which actually is only true. The other form he wrote it down is only true when C satisfies the triangle inequality. But that wasn't what he meant, because at the end of the article, he says, of course, the case where C satisfies the triangle inequality is the one of most interest. So that was kind of really weird to me. This is the general version that works whether C satisfies the triangle inequality or not. And the first place that I've seen it written down is in the paper of Kuhn and Tucker, where they talk about the Kuhn-Tucker conditions for solving linear programs, which is a discrete setting. Now, of course, a lot of people wrote about these problems in discrete settings, and I think in some sense, Kantorovich gets a lot of the credit because he was one of the first people to consider it in the general metric space setting, which is much more flexible for a lot of applications. You want to move air masses around, you probably don't want to think about discrete molecules of air. So this is sort of a miraculous theorem. Half of it's easy to see. The half that's easy to see is that if I have a u and v that satisfy this inequality, and I have a gamma in, so So gamma in having the correct marginals and U and V such that I'll write the sum, meaning they're evaluated on different spaces, implies what? It implies that I can integrate this non-negative function C of xy minus ux minus vy against gamma. So this is a non-negative function, and so when I integrate against a non-negative measure, I get something non-negative. But that's of course the integral of c d gamma minus the integral of u d gamma, but u only depends on x, and the left marginal of gamma is mu plus, and so that's like integrating u against mu plus. And similarly, this v only depends on y, so the other integral is like integrating v against mu minus, precisely because gamma is in this set with whose marginals are constrained. And so that tells me that that the integral of c d gamma is always bigger than the expected value of u d mu plus v d mu minus. And so then even if I maximize on this side and I minimize on this side, I'm still going to have, so this inequality is obvious. And somehow the miracle of duality that we'll talk about more about on Tuesday is that equality holds. But what I'm going to do today, so on Tuesday, I'll try to give you some intuition as to why duality holds. What I'm actually planning to do today is show you proof. So that's kind of backwards. Usually you give the intuition first and show the proof later. But somehow the proof that I'm going to show today, it works when C is continuous and mu plus and mu minus are compactly supported. It can be adapted to some slightly more general cases, although it's not the most general proof ever. But it's strongly inspired. This proof is strongly inspired by Brenier's theorem. Okay. So let me set this. And if you've studied linear programming, those of you who studied linear programming before have seen an analogs of this kind of duality in the finite dimensional setting, where you're minimizing a linear function on a convex polytope. But this is a case. This was probably the first infinite dimensional case of duality, at least that I know about. Great. So so I'm going to show you proof, but the proof doesn't give you, or at least it doesn't give you the simplest intuition into why this duality should hold. And another way to think about this duality, so you often flip the signs on this problem. So you often set C to be minus B, cost or benefit, right? And you try in some problems you try to maximize the benefit instead of minimizing the cost. And a way, if I flip the signs on everything, then let me call u tilde and v tilde the negatives of u and v. So then u tilde plus v tilde would then be bigger than b. And there's a kind of economic interpretation for this condition of bxy being less than u tilde of x plus v tilde of y that comes out of matching theory, where you're trying to match residence with residency programs or something. And the benefit of mapping resident X with program Y is B, and then they negotiate on who gets to keep what share of it. And so U tilde would somehow be the share that's kept by resident X, and V tilde would be the share that's kept by program Y. And you want this inequality to hold, because if it went the other way, then the shares would be too small. The share that X is getting and the share that Y is getting would be less than what they could get if they matched with each other to generate benefit D, and that would be an instability. So going backwards is an unstable match. And somehow that's the intuition from this economic matching problem is that if every X is trying to maximize their U tilde and every Y is trying to maximize their V tilde, that's this problem, and that the solution that you get in this special framework is the same as if somebody comes along and says, never mind, the individual is trying to maximize their thing, I'm the social planner, and I'm the company in Boston that does the allocation of US medical graduates to residency programs, and if I just try to maximize the total benefit over all possible permutations of residence with respect to programs, I will achieve the same outcome as if we let the individuals negotiate. Somehow that's what's, I guess in the economic theorem, that would be called the second welfare theorem or something like that. Okay, great. So let me sketch this proof that leads us into Brenier's theorem, but the proof's going to come in several steps. And the first one is to understand, if I attain the minimum of C in the Cantor-Roach problem, how does the supportive gamma look? And So let me introduce a terminology. So S, if I take the support's going to be a subset of the product space. So if I take a subset of the product space, it's going to be called, I'm going to maximize benefit instead of minimizing cost. So it's going to be called B cyclically monotone if and only if, whenever I choose a natural number n and a collection of points in the set, the sum, I find that the x's are paired with the y's, 1 up to n, in such a way as to maximize the sum over all permutations of partners. Right, so for every permutation sigma on n letters, if I permute the given y's with respect to the given x's, I never get as much benefit as if I keep them with their own partners. That's what it means for a set to be cyclically monotone, cyclically monotone. And then the theorem, and this is again, if B is continuous and support mu plus and minus are compact. Then, but again, these hypotheses can be relaxed, but this is just, I'm just trying to talk about the simplest case today. Then if gamma achieves the maximum, so if I look at all gamma tildes with given marginals, and I try to maximize integral B against gamma, if gamma tilde rather, then if gamma achieves the maximum, then the support of gamma, which is now a subset of the product space, is B cyclically monotone. Is the statement clear? And the idea is that, so in fact, so let me make a few remarks. Actually, this theorem is if and only if, but I don't plan to prove the converse direction yet. The converse direction will follow later. I plan to prove the if direction, which is the more, either it's the harder direction or it's the more interesting direction from our point of view at the moment. And the intuition behind this theorem is that if the m plus is here and the m minus is here, and I have the optimizer gamma, and I take a bunch of points that lie in the support of gamma, they're like pairs x1, y1, and x2, y2, and x3, y3. And what it means to be in the support of gamma is that every neighborhood of these points has positive mass for gamma. And what it means to be cyclically monotone is if I somehow, if instead of sending from x1 to y1, oops, I sent from x1 to y2. So if I should change colors at this point. Suppose I did this instead, and I did this instead, and I did that to compensate. So somehow the projection, the horizontal and vertical projections of the blue boxes is the same as the horizontal and vertical projections of the green boxes. And so the idea would be if I subtract mass from the blue boxes and I add it to the green boxes in such a way that I don't change the marginals, I don't change the horizontal and vertical projections, then if this inequality were going the wrong way, I would be able to create a measure with generating with the same marginals, but generating larger benefit than gamma. And that's a contradiction to gamma maximum, attaining this maximum. And so now, is the intuition, are there questions about the intuition? I'll sort of write down something that's closer to a proof, but let me just, hopefully the intuition is clear first. Okay, great. So how does the proof go? So the proof goes, I guess we can start it here and continue on the next page. Maybe I'll do it in green, who knows? So the proof is let, for a contradiction, suppose gamma is a maximizer, but doesn't have V-cyclical monotone support. That means that I can find an integer n, a sequence of points in the support of gamma, such that this inequality goes the other way, right? So then there exists an n and x1, y1 up to xn, yn in support of gamma with and a permutation on letters such that this inequality goes the wrong way. And well, okay, so if I go back to the, so actually permutations can always be written as products of cycles. And so if this inequality goes the wrong way, then for one of the cycles in the permutation, this inequality goes the wrong way. So let's just focus on that cycle. So this, I don't need, this could be I+1. And provided that I make the notation that xn plus 1 is x0, or rather yn plus 1 is y0, or is y1 rather. And since v is a continuous function, by assumption, that means this will continue to hold in the neighborhood of these points. Also, to neighborhoods ui cross vi of xi, yi. And because since xi, yi is in support of gamma, that implies that gamma is positive on these open neighborhoods, right? If gamma was 0 on one of these neighborhoods, then I could have taken a smaller closed set and still having the full support of gamma. And so now I kind of need to define, remember I had the little blue squares, I need to define the restriction of gamma to each of those blue squares. So let gamma hat I be, so I'm gonna, let me say a bit of notation is that mu plus restricted to A of a set B is basically mu plus of A intersect B. And so I'm going to let gamma hat I be the restriction of gamma to ui cross vi, but I want it to be a probability measure, so let me divide it by mi. And I'm not dividing by 0 because of this. That's the restriction of gamma to the little blue square. And I can, the point is that gamma minus mi, gamma hat I is still non-negative. Now, if two of the little blue squares overlapped, I might have, and I wanted to subtract both of them, I might have a problem. But it's also true that gamma minus, if I divide by the number of squares, then I don't have a problem anymore. It's still non-negative. And so that tells me that as long as I don't subtract more than mi of each of these probability measures, I'm not going to make the measure negative. I'll still have a non-negative measure. And so that's going to allow me to subtract out the blue squares. I also need to add back in the green squares. And so it's very convenient to use push forwards to represent all these measures. And so there's a sort of standard nice trick. And the nice trick is I can represent gamma hat I as the push forward of, let's say, xi cross yi, push forward omega for every I, where, let's say, z omega is some probability space. And the idea here would be, for example, take z to be the product of m plus and m minus with itself n times, and take xi, yi of this x1, y1, x2, y2, up to xn, yn, to be the xi and yi. That would be one way to do it. And I would put, and then I would put the product measure, take omega to be gamma 1 hat, product gamma 2 hat, product all the way up to gamma n hat. And so then what you can check is that if you push forward this product measure through the ith pair of mappings here, you get this guy back. But so this is somehow the construction that's in the background, but I don't need to know it. What I need to know is that I can represent them all on the same probability space. And here we did finite dimensions. I think Kolmogorov or somebody tells you that I could even handle infinite products, but I don't need to do that today. And then so how do I, so then basically the idea is I would write down a perturbation, gamma epsilon would be defined as gamma minus epsilon times the sum of the I counting from 1 to n of the gamma I hats. Those are the blue squares I want to subtract out, but then I want to add something back in. Another way, maybe it's better that I write the gamma I hats in the form xi cross yi push forward omega. And then I want to add back in the green squares, and the green squares are basically the xi cross the y sigma i's. Push forward omega. So this is the perturbation that corresponds to subtracting out the blue squares, adding back in the green squares. And as long as epsilon is less than 1 over n times the min of the mi's, this will be a non-negative measure. And the point is it will have the same marginals as gamma. So the projection onto the first factor, I guess I called it P, px of gamma epsilon is going to be px push forward gamma epsilon is going to be px push forward gamma, which is mu plus, minus epsilon times the sum of the first factor is going to be xi push forward omega minus the sum of, I guess it's going to be, in this case, it'll be xi again, push forward omega. And these sums cancel each other out. And if I do the y projection, so this is mu plus. And if I do the y projection, then I get mu minus here, minus epsilon, and I get the sum of the yi's, push forward omega, minus the y sigma i's, push forward omega. And now in the first sum, they cancel out term by term. Now they don't cancel out term by term, but the entire sum, because this permutation gets all the guys between 1 and n, the entire sums cancel out. So this is still e minus. So for epsilon small enough, this is non-negative, and it's a legitimate permutation, or a legitimate perturbation rather, of, it's still in the same set of candidates. And you plug in the cost of this gamma epsilon, and you see that, if I go back to the previous slide, you see that because this inequality extended to this neighborhood, the cost of this gamma epsilon is actually or the benefit of this gamma epsilon is actually larger than the benefit of gamma, and that's a contradiction to the maximality that we assumed of gamma. Gamma was supposed to be a maximizer, right? So cost of gamma epsilon is basically, gamma epsilon was the gamma, the cost was linear, plus a sum, I counting from 1 to n, of, oh, sorry, it's benefit. I'm doing benefit, which is minus cost. A sum of what happens when we want, let me go back to one slide. When we want to integrate the benefit against a term here, we get the xi yi. And when we want to integrate it against a term here, we get the xi y sigma I. So so we're going to get the integral b of xi yi. I think it was minus epsilon, integral b xi yi d omega minus, let me write the d omega outside. Okay, well, minus b xi y sigma I d omega over z. And our assumption about the sum of, so since xi yi is in ui cross vi, our assumption was that, I've written this in a poor way, but let's not put the sum, let's put the integral outside. D omega over z. This thing was assumed to be negative, and so because of this minus out front, the whole thing is bigger than benefit of gamma. And that's the contradiction we wanted. So the questions? Okay, so that's great. So now we know the gamma, support of gamma is characterized by this property of bicyclically monotone support, which is maybe not that surprising when we think about the discrete analog of the problem. And now there's this beautiful theorem that, so in duality, we said there were these sort of, the individuals got payoffs U tilde and V tilde, the pair got payoff B, and there was an inequality relating the sum of the U tilde and the V tilde to B. And so somehow I would like to deduce the existence of this U tilde and V tilde, which achieve, we also said in this duality statement that one inequality was obvious, but we want to know that equality holds. So I'd like to produce a U tilde and a V tilde that achieve equality. And there's a theorem of Rockefeller and Roche and Chonet. Sorry, just Chonet rather. So this was proved by Rockefeller in the 60s in the special case where the benefit is x dot y and the m plus and minus are both Rn. And it was extended to this more general case B by Roche in the late 1980s in an economic context. And so what does it say? It says, oh yes, I need a definition before I state the theorem. So the definition is, given U a possibly infinite valued function on M plus, define the B subdifferential, what's called the B subdifferential. or at least I call it the B subdifferential for sort of historical reasons. I'm going to use some funny notation, but it's basically the set of all pairs x and y in M plus cross M minus, such that U at any point is bigger than UX plus B XY minus, sorry, B at that point, let's call this Z. B of ZY minus B of XY. And this should hold for all Z. And this definition is actually motivated by this case here, because in this special case, the expression is that U at any point is bigger than UX plus, by linearity of the inner product, it would be this point minus X against Y. And so this looks like a little bit like a Taylor expansion of U around X with slope Y. And so it says that this linear affine function, which looks like the Taylor expansion of U around X with slope Y, is a lower bound for U everywhere. So in particular, if U is differentiable, Y would have to be the derivative of U in order to, for a Taylor expansion, you need a term that asks for little o of dot minus X here. And here I'm saying that the inequality holds even without this little o correction. So on the one hand, this is like Y is some kind of generalized derivative of U at X. On the other hand, I'm not only asking for this to hold locally near X, I'm asking for it to hold globally. So that makes it a stronger notion. So that's why it's called the subdifferential. And the theorem of Rockefeller, Roche, and Chenet is that if S has B cyclically monotone support, if S is B cyclically monotone, then it states the existence of something. There exists U on M plus, possibly taking an infinity as a value, but not identically equal to infinity, such that S is contained in the B subdifferential of U. So you can take infinity some places, but not everywhere. And then I have this containment. And let me see how to think about this theorem. Yes, again, in this special case here, there's a nice way to think about this theorem. And but maybe since we're running out of time, let me prove the theorem first, and then somehow that seems to be my modus operandi today. Instead of giving the intuition first and then the proof, I'm going to give the proof first and then the intuition. But so this U that this theorem asserts the existence of is going to be the U that achieves the minimum that was dual to the maximization in the Kantorovich duality statement. And this is basically, in this case, you can think of this as a theorem about integrating vector fields. So if you had a vector field Y defined for every X, you would like to find a function, actually a convex function, whose derivative at X is equal to Y, or at least for which the slope Y is a supporting hyperplane at every X. And that's what Rockefeller showed you could do in the 60s. And this is what Roche showed you could do in this more general sense for arbitrary B in the 1980s. Questions? And so basically the proof is by construction, and it's sort of it's a clever construction, but it's not, the proof is short, but clever. So let me show you this clever short proof. Oh, and before I show you the proof, let me say this theorem is actually if and only if as well. So the obvious direction is whenever you have a function U not identically infinity and you define the subdifferential, you can check that the entire B subdifferential is in fact B cyclically monotone. It's easy to check. The converse is the tricky direction, which is that whenever you have a B cyclical monotone set, you can find a U for which that cyclically monotone set is contained in the B subdifferential. Okay. So the proof is to fix some point x naught, y naught in S. Just like when you integrate a vector field, if you have a conservative vector field, meaning its integral around every loop is 0, that means it's the gradient of a function. So when you want to recover the function, you pick an x naught, and when you want to, you can set the value of the function to be 0 at that x naught. For any other x, you can integrate the vector field along any curve you like to figure out what the value of the other x is. So here we're going to do something general, analogous, but it's going to be kind of this discrete flavor. We're going to write down sort of a Riemann sum instead of an integral that relies on the B-cyclical monotonicity condition. So for every other point x, I'm going to define u at x to be a supremum over integers n, and then a supremum over n tuples of points in S of a funny sum like we saw before. I guess like the sum of b, let's say, xin plus 1 yi minus bxi yi. And the sum will count, I guess, from 1 up to n. And with the convention that xn plus 1 is going to be x in this sum. Right? All the other guys are defined here. The last guy is going to be this point over here. And so let's see, why does this construction do the trick? Well, so actually the hard part is to show that, so there's two steps. And the hard part, what you might worry about is that I'm taking the supremum over this enormous set. I might get plus infinity. And so claim 1 is that u of x naught equals 0. And that basically prevents me from getting plus infinity, in which case I would have a nonsense construction. And then step 2 is that the B subdifferential of u contains S. And in fact, step 1 is the hard step and step 2 is the easy step. Or what should I say? In step 1, we're actually going to use the B cyclical monotonicity. So in step 1, why is step 1 true? So the B cyclical monotonicity of implies that this entire sum here is negative, I guess, for any of these choices, because all of these points plus this guy are in S. And basically what I'm looking at here is some permutation of partners. Here it's a permutation of x's with respect to y, but that's the same as permuting the y's with respect to the x's. Do I believe that? I might have to add one or two more terms. So this entire sum, I probably want to write also somehow y0 should come into it. This sum plus minus bx0 y0 and plus by0 x1 is negative. And so that means that without this extra term, this is less than b x0 y0 minus bx1 y0. Okay. So at least, maybe I didn't show it was 0, but I at least showed it was bounded above. I think it's actually 0, but anyhow, what I showed was it's bounded above because these are both finite numbers. And for the second step is actually easy. So the second step is I want to fix some fix x, y, and s I want to show that xy is then in the subdifferential. So what it means is that for every epsilon bigger than 0, and when I put this x in here, there exists an n in a chain where I get almost this large. So there exists an n and a sequence of points, x and y n, in S such that ux is less than epsilon plus this sum. And now I want to let z be any other point in M plus, and I want to show that uz is bigger than ux plus b of z y minus b of xy rather. And this is giving me the lower bound on u that's going to lead to that up to this error epsilon. And so how do I get this? Well, the competitor that I'm going to take in the definition of uz, now I'm going to change this to z, but I'm going to look at a chain of length n plus 1 where the n plus first point is xy. So now this is going to be xn plus 1, yn plus 1 for the same n and the same first n points. And I know that, so this is what I want to show. And what I know is that u of z is actually bigger than the sum I counting from 1 up to n plus 1 of bxi. This is now n plus 2. So I plus 1 yi minus bxi yi. And so this is b of z yn plus 1, which is y, minus b of xy, plus the first n of these guys. But I know the first n of these guys are, let me make this bigger now, than ux minus epsilon. And so I got the inequality I wanted, this guy here, up to an error epsilon, but the error was arbitrary. And so finally, by letting epsilon go to 0, I get the inequality I want. And so that's the proof that whenever you start with a bicyclically monotone set, you can create a potential whose B subdifferential contains the set. And you should think of this construction as being strongly analogous to u of x equals u of x naught plus integral from x naught to x of, let's say, y of x or v of x dot dx. So integral along a curve, in the special case, b of xy equals x dot y. And this integral here gets replaced by this kind of Riemann sum. And well, there's the supremum, but that's because I'm living in a discrete world, in a world of inequalities instead of a world of equalities. So I'm now basically out of time, but I do have time to take questions. And maybe I will stop the recording at this. So the analogy is, if I had a vector field V taking Rn to Rn, and if the integral around every closed loop of V dot dx was 0, that would tell me that my vector field V was actually the gradient of a function, right? That would say that there's a C1 function. If V was continuous, that would say there's a C1 function U such that V is gradient U, right? This is what it means to be a conservative vector field. And in a simply connected domain, conservative vector fields can be integrated. They come from potentials. And so, and how do you construct the potential? You fix an x naught and you set the U to be, let's say, you could, whatever value you like it, you could set it to be 0 at x naught. And then you integrate along any curve you like from x naught to x, v of x dot dx. And you might worry, does this integral depend on the choice of curve? But the fact that integral of v around a closed curve gives you 0 says that it doesn't depend on the choice of curve from x naught to x. And then you check that when you make this definition for u, the derivative of u is, the gradient of u is given by v. That's sort of what we do for our second year calculus students. And so I'm saying this is a kind of an analog of that, a rather nonlinear, unless B is bilinear, this is a rather nonlinear global analog of that statement in second year calculus, where instead of arbitrary curves joining x naught to x, we look at arbitrary sequences of points, xi, yi, that start at x naught and end at the x we're interested in. And the yi here is the stand-in for the conservative vector field. Other questions? So for those of you that weren't here in the first lecture, I basically said that I would hang around after class every lecture for as long as there are questions to kind of run a virtual office hours. So I will now transition into virtual office hours, and anyone that wants to leave can leave.